Jamba just woke up. Alright, what? November 17th. Alright, yesterday was bad. Was not able to do it. So I think today. I even gave it some thought. And I know why it didn't work yesterday. Like my idea of grouping them together. Yeah, I know why it didn't work. Um, so there are two ways we can deal with this. One is we read this, but I mean, it's not really helpful. Binary search. I thought about binary search. I was using sliding window. I did not use prefix sum. I definitely did not think about a monotonic queue. So one way is we read this and try it again. For example, think about how we can use a heap to help this. That's one way. Or the other way, we just go read through the solution. There are two ways to approach this. I'm not sure which one I want to do, honestly, but we do have some new examples, so maybe this can help. And I think I have another example. I think that's the only example I have, right? So I can read this example and then try to see if there is a way to do it. Or you can say, why do we need a priority queue? A priority queue for what, right? That's quite important. What's the priority queue gonna be good for? I don't know. I mean, that's the thing. I don't know. So maybe we should just go for the solution. And I know there are 3 or 4 out there, so we can go through them and then implement, right? That's usually how we do when we fail. But let's get through today's first. Hopefully it's very straightforward. We're bound to diffuse. Your time is running out. Your informer will provide you with a circular array code, but you don't know from where, right? To decrypt the code, you must replace every number. All the numbers are replaced simultaneously. If k is a key larger than 0, replace the ith number from the sum of the next k numbers. If k is smaller than 0, then replace ith number with the sum of the previous k numbers. If k is equal to 0, replace ith number with 0. The code is circular. The next element of this is going to be here, and the previous element of this is going to be here. So we're going to return the decrypted. Okay, so for this is the next 3, right? And for this is the next 3. So it wraps around, but I think a prefix sum can handle this, right? If we do prefix sum on this, we have 5, 12, 13, and 17, right? So for 5, I need the sum of this, basically 17 minus 5, so we got 12, right? So for this, I need go 3, but we don't have 3, but we know we have 2, right? So we basically need these 2, which is 5, plus is 5, that'll be 10. Here is this 4 plus 12, right? So I think it is a little bit of maneuvering around that we need to do. But usually if I want the next 3, so I just add 3, right? Plus 1, plus 2, plus 3, and minus myself. This is the next 3. Until we cannot, right? So basically we can do is, if we go to the end, we have this, and the remaining we put in the front. Okay, so that's that. Well, if k is smaller than 0, it should be the same, right? Smaller than 0, we just look minus 1, minus 2, minus 3, right? Minus 1, minus 2, minus 3. And then we want this is going to be, actually, it's slightly different because it's going to be this minus the front, right? This minus the front. That actually make me wonder if we want to create another. I don't think I want to create another. Yeah, this minus the front, so we can get those. And then if we move to the front, then we need to wrap around. So it's just going to be the front, right? The front, which means the one you go -1, -2, minus k, right? -1 is to minus k. Actually, we can try it. So we have an example. 2, 4 is going to be 6, 15, and 18. Right. So we do this. We start from here. So we go -1, -2, -3. Can we? I do not think so. So -2, 1, -1. So we have this, and then we do -2. So a bit negative. So that's not gonna work. Then we try to see how many we can have here, right? How many we can have here. Zero. We have 0 here, right? So we know here we just need to go how many. So from this side, we go same thing, from n minus 1 and -2, right? So we have to end at this. So what we do is the end minus this minus 1. So it's going to be 12, right? And then we go here. This one is still a no-go, right? However, this one we will end at, because it's 0, 1. 1 minus 2 is -1, right? -1. Which means this gives you how many more, right? Like this 1. We need 1 more from this side, right? 1 more from this side. So you know we have 1 here, and we will do this by itself, right? We'll do this by itself. Okay, this -1. We'll do this by itself, because this -1 is the starting position, right? The starting position. If the starting position is -1, then we don't do anything. But the starting position is 0, so we have 2. And then we need 1 here, so this is going to be 3. So it'll be 5. Right? This will be 5. And then we move on here. Then -1 is 2. So this gives you 0. Right? Because 0, 1, 2. And 2 is 0. That means we can handle it. Right? We can handle it. So there will be this minus this -1. Right? And then because this -1 is a negative, so we don't consider, so it'll be 6. And here will be 0, 1, 2, 3. 3 minus 2 is 1, so we say we end at a 1. And then the previous one is 0, so it will be this minus this will be 13. So yeah, I think we can get the logic out. Shouldn't be too hard. Let's take a look. Right, let's just take a look. Shouldn't be too hard. So what we need to do is we need a p-sum. Right? And then we say p-sum 0 is equal to code 0. And then for int I, 0, I smaller than code.length, I plus plus. So what we're going to do is we say, actually we don't need this, we can just say p-sum I equal to p-sum I minus 1 plus code I. Okay, so now we have that, and we have k. So we're going to do an int res new int code.length. Okay, and then for each one, int I, 0, I smaller than code.length, and then I plus plus. Right, what we're going to do is if k is larger than 0, and if k is equal to 0, right? Oh, then we don't have to do it. Oh, we can actually do this. If k is equal to 0, right, and then we just return res. Done. So if k is larger than 0, okay, so now we have to do a little bit thing about here. So we can say the and. So we can say and will equal to I plus k. Okay, I plus k. So and then if n is smaller than code.length, right? So which means we are all inside. Then we can say res I shall equal to p sum and minus p sum I. Done. Else, if n is larger or equal to, right? Larger or equal to, then we can find out how many addition that it will need. Then we can say res I shall equal to p sum code.length. Actually, I have done code.length so many times I kind of don't like it anymore. So we can do this, and then we say code.length, right? And then we'll replace with n. So replace this with n. Oh, I cannot do that. Okay, so I will do this code.length. Okay, of course this one has to change it back to code.length. So yeah, this is good, this is good. This is going to be changed n minus 1 minus p sum I plus p sum, what is this one? This is n minus n, okay? N minus n, so if it is the length, that will be 0, right? So we'll plus this. Okay, yeah, that's that. Good, I think we don't need this one anymore. Okay, so that's if k is larger than 0, right? Else, if k is smaller than 0, then we can say in the start is I minus k, right? In the start is I minus k. Then we say if start, because minus 1, minus 2, minus 3, right? So if start is larger or equal to 0, then we know wraparound. So we say res I shall equal to p sum p sum I minus 1, right? Minus start is equal to 0. If it's equal to 0, then we'll do 0. Otherwise, should be p sum start minus 1. Okay. Else, now this is when we need to wrap around. So it's smaller than 0. Okay, it's smaller than 0. So we have p sum I minus 1. We have to include everybody, and we have to plus something. Okay, plus something. So plus something is the st, because it's minus k, right? So if I have a negative, so whatever negative need to be on the other side. So we can say p sum basically here is going to be n minus 1 minus p sum something, n minus something. Okay, so I can say n, maybe n plus st. I'm not 100% sure, because let's say st is negative 2. Like say I is 0, right? I is 0, k is 2. So st is negative 2. So st is negative 2, which means we need two things from the right hand side. So we have this minus 1, minus 2. So that's actually not right. We need minus 1 one more time, right? Minus 1 one more time. Okay, edge case. I'm 100% sure there will be lots of edge cases that we need to handle. So edge case number are these even possible. Like this I think is possible, but these two are possible. This is possible, n minus n, and that is something, it may not be possible. Hold on. N is I plus k. What if the k is super duper big? So what's the condition of k? So k is within the range, so k will not be super duper big, right? So k at most is n minus 1. So I plus n minus 1 is the end. And if I'm at the end, like if I is at the end, and I is n minus 1 plus n minus 1, right? So 2n minus 2. So 2n minus 2, and then we need to basically wrap around. We say it's gonna be n minus 1 minus this. That's actually gonna be 0, right? And p sum n minus 1, 2n minus 2, n minus 2. I think that's correct, right? I think that's correct. Okay, I'm worried about this one. This is, st is logical to 0. This one should be fine, unless I is equal to 0, right? I is equal to, what if I is equal to 0? Well, if I is equal to 0, st must be smaller than 0, so this one should be fine. So if I is equal to 0, st is smaller than 0, right? Then we'll have, yeah, what if I is equal to 0? Right, so here is the thing. We should say I is equal to 0. If that's true, it would be 0. Otherwise, if I is not equal to 0, then we have something here. And plus, then we wrap around. So n plus st. So st, the smallest will be minus n plus 1. So minus n plus 1, it will just be 0. And it'll just be everybody. Okay, I think this looks decent, so we're gonna try it. I don't feel this, I think this can, I mean, it is easy in terms of logic and stuff, but I don't think it's easy to implement. We call it prefix sum. It's the ideal is simple, but the implementation requires some thought, right? Of course, it's easy. Another reason is because the constraint, right? The constraint is pretty only 100, so you can essentially go with you see that this is the thing, small errors causing the issue. The implementation wise, it can be really tough, really tough. Now we have a -1. What happened here? Oh, dang, this is plus, because k is smaller than 0. Shoot. All right, let's give it a shot. Hopefully we handled all the cases. Yes, we did. Oh my god. Yes, we did. Yeah, this is not easy, man. I don't think this is easy. You have to consider all the situations, and then there are pitfalls. I like this one. Yeah, you can brute force sliding window. Oh, sliding window. I didn't think about sliding window. Wow, it is sliding window. Damn. Okay, I was not. Yeah, we get a new starting point, and we get n equal to k. Yep, and then okay, we get a window sum, and then starting here, this will be the sum minus this plus this. Oh yeah. Alright, I'm not gonna change because, but I did not think about sliding window. That's the truth. Alright, so I still don't want to completely rely on the solution, so I'm just gonna read through it and see how this one's done. Okay, we're given an array, nums, that contain both positive and negative, yeah. We have negative value. We strongly suggest solving the origin. This one is, we can use the sliding window, right? Yep, that's exactly right. This one is easy, very straightforward. We done it. I think I got it. Yeah, I checked. Let's identify the redundancies in the above approach. One major issue is that we keep recalculating the same subarray sums multiple times. We can solve this by creating a prefix sum array. Yes, which lets us quickly find the sum of any subarray. Yeah, I can do that. You can look at each element and find it. We can look at each element. Okay, we have each element and find an earlier prefix sum. That earlier prefix sum. Oh, it doesn't matter. It could be a later prefix sum. That when you add to it, when subtracted from the current sum, gives us a value at least of k. Wait, hold a second. Let me read this one more time. Oh, I think what it's trying to say is if you have a prefix sum, right? If I have a prefix sum of, P0, P1, P2, all the way to Pn minus 1, right? You have all this. And I want to know a subarray ending at P2, what's the smallest such that its sum is larger or equal to k? That means P2 minus some Px, where 0 small equal to x. Well, we're actually going to have a 0 here. So that's P0. Okay, that's P1, P2, P3, and then P. It doesn't matter. So right. So 0 small x is smaller than 3, right? So I want to find among these which one allow me to do this minus this such that it's a larger equal to k, right? So we're going to find this px, and we want to find the px, eligible px with the largest x. So I know p3, I know k, so we can say px must be smaller or equal to p3 minus k, right? p3 minus k. So I have all of these in the front, okay? So I want to find one that its value is smaller than this, p3 minus k, okay? Value is smaller than this, smaller or equal to this. So the smaller the better, okay? So smaller the better. And among all of those, I want to have the largest. How do you express that in priority queue? Because priority queue can only order on one of them. You either order on the value, right, or you order on the on x. But x. What if we have a monotonic decreasing? So when you look at it, but a monotonic decreasing, the thing is with a monotonic decreasing, if let's say this is big, and we'll pop everybody, right? Okay, there is one way, binary search. If we put all these sorted from small to large, right? Then I do binary search for this, then everybody in this range, but I still need the largest index among these. Okay, I still don't know. All right, so far so good. However, searching for the best prefix sum for each index is still too slow. What we really need is a way to quickly find the best prefix sum, one with the lowest value that's also closest to our current position. Exactly, that's what we need. This is where a heap count becomes helpful. So are you saying that we will create a variable for the heap to compare, which takes into consideration both the prefix sum and the distance away from? That is not true though, right? That is not true. That is true because I have prefix sum, we want this to be small, and I also have the index, I want index to be big, right? Index, I want a big index but with small value. So the one with the biggest index with the smallest value shall rank the first. How do we create a ranking for two variables at the same time? Okay, let's loop over the nums array now. Keep tracking of the running sum. Okay, I have a prefix sum. We also keep track of our result in the variable shortest length. If the cumulative sum meets our constraints, we consider it as a potential result. Otherwise, we'll loop over the top element of the heap while the difference between cumulative sum and the sum of the top element is larger or equal to k. For each such element, we check if it is the minimum length subarray we've found until now. After checking an element in the heap, it can be discarded since all further sums will result in longer subarray and can never be the answer. Once we've exhausted all valid previous, we can add a current. So you're telling me that we're just going to stop popping everything in, and then you say After checking an element in the heap, it can be discarded, since all further sums in the loop will result in longer sub. Actually, I don't understand this one. Okay, let's take a look at this. All right, empty, and then we current index. Okay, nums 2 to cumulative sum. Since 2 is smaller equal to k, no valid subarray yet. And also valid subarray. Okay, so priority queue we have this and this index. Okay. So prefix sum is 1. So we add 1 in it. Cumulative sum is larger or equal to k. Update the shortest length to 3. Yes. And then we put this one in. But in this position, we need to look for P3 minus, or P this, right? Minus 1 minus 3. So it'll be minus 4. We need to see something minus 4, but it does not exist, right? So if this would be something, yeah, that also does not exist. Unless you want 0. 0 can exist. And then you have here 2, you have 3, right? And you want to see if 0 exists, but 0 does not exist. Well, technically you can put a 0 in. So yeah, so you can handle it. Check heap 3 minus 1. So the smallest, right? Smaller than k, so we'll keep element. So we don't use it. We do not use it. So we find the smallest, right? So of course, like for 2, you require something to be smaller than smaller equal to minus 1, right? No, smaller equal to 0, because current is, you need a smaller equal to 0, and they don't have, so of course you don't do it. Now the next one, and you put this one in as well. So next, you have this, right? Comes with 4, so you won't find something that's smaller equal to 1. So you got this pop up, but that doesn't explain. Well, what if I have another one? I have a 1 at before and I have a 1 at the end. I have 2, right, 1s. I think what it's trying to say is you pop all of them. You pop everybody that is smaller than you, than the requirement, right? So let's say we have a current prefix sum, right? I have found, we're using this, you can do, because everybody who is smaller than p minus k will be at the top, and then you pop it out, right? You pop it out, and you can find the length. What it's trying to say is once those gets popped out, they don't get put back in. Why? Well, because if I have in the future a prefix sum that is even bigger, right? That is even bigger, and a bigger p will result in a higher threshold, right? So all of those will be included, right? All of those will be included, but then the length will be longer. So that's correct, the length will be longer, so those shouldn't count. And if I have something smaller, right, than the p, than the current p, then my threshold will be lower than those. It does not matter, okay? It does not matter. All the things in the priority queue will only be used once. Whenever the current is be used, that's it. Because if you want to use the same thing later on, you will create a longer subarray, which is, no, you already have something. That is absolutely brilliant. Absolutely brilliant. I cannot express how amazed I'm at this solution. It's absolutely brilliant. Amazing. Amazing solution. We don't even need to have a prefix sum array. We just add them to it, and then we shall be able to go. Wow, that is great solution. That is great solution. All right, we need to implement this, but probably some other time. But this is great. This is great. Hey, and there are two more things there to go. This one also, I have so many backlog. Yeah. All right. I will see you guys tomorrow.